Hello, in today's lecture, we are going to start with the new topic. However, we've done a good amount of multiple expansion till now, but still a few lectures are awaited or probably need a certain advanced treatment. Uh, right now, I'm suspending that for a while, and I'm going to start an interesting topic today. And this topic is also very mathematically intricate. However, all the mathematical intricacies I'm going to address later on. But right now, I'm going to start with a slightly one. You can take it as a fact, or you can take it as a uh, one of the takeaways from theorems called as uniqueness theorem. So basically, we are going to do uniqueness theorem, but we are going to do it later on. But today, let us see one of the most important consequence of uniqueness theorem. And after knowing that, you will be able to do these problems in a slightly better way. So without wasting time, I'm going to start today with something called as method of images. Okay. But before method of images, let us first understand what do we mean by uniqueness theorem. So I'm right now not getting into this. I'm just going to write a few statements on which your method of images is based. And then we're going to start with method of images mostly. Okay. Okay. So as I have mentioned in Laplace's equation also, in Laplace's equation, we've seen that there can be many solutions to Poisson and Laplace's equation can be non-unique. That I mentioned very initially also. Solution to Poisson equation or Laplace's equation are many. So there are many solutions to Poisson or Laplace's equation. However, in physics, we are interested in those solutions which satisfy our initial boundary conditions. So in physics, we are interested in finding solutions which satisfy the boundary conditions. Okay, which satisfy the boundary conditions. Okay, so which satisfies the boundary conditions. Okay. So what happens is that once we know the boundary conditions, then the solutions to the Poisson equation or Laplace's equation are then unique. Okay, so are then unique. That is, I can say that what does uniqueness theorem like? All these things are very mathematically. I'll solve them lately, but right now we're going to use these statements for doing a mathematically relevant, physically relevant problem called as method of images. Okay, so basically understand that among various possible solutions, this this of Laplace's equation or Poisson equation so among various solutions of Laplace's Poisson equation, the solution which satisfies boundary conditions are unique. The solution that satisfy boundary conditions are unique. Is unique, sorry. Okay, so always remember this part. Now you can have your boundary conditions can be posed up. So you can another way also say that, like for example, if I want to say the same statement that no two solutions I can write different can satisfy the given equation with specific boundary condition. There can be no two solutions. There can be no two solutions which satisfy a given equation with specific boundary conditions. And Although again, I'm saying that this is a very I'll take a good amount of time in this also, but right now, again, I'm saying that it is going to be more or less restricted to one of the problems in physics that is called as method of images. So all these statements, we are going to just use them up. So there are a few, like by name, you should remember. One is called as Dirichlet boundary condition. One is called as Dirichlet boundary condition. What is Dirichlet boundary condition? That, for instance, we want to find a solution in a volume V. We want to find a solution in a volume V, which is bounded by a surface S. And within within this surface S, we have different conductors. Conducting surfaces. Let's say S1, S2, S3. So within this volume, which is bounded by surface S, there are different conductors S1, S2, S3, on which we know the value of the potential. On which we know the value. I'll write value of the potential is known. Yes, the value of the potential is known. Additionally, potential is known on the surface itself. So I'll write potential is also known on the surface itself. Okay. So these kind of conditions, this kind of boundary condition is referred to as the Dirichlet boundary condition. Okay. I mean, I'm just giving you some definitions. Okay. Now, instead of potential, if we are supplied with electric field, okay, if instead of potential we are supplied with electric field, these conditions will be known by the name called as Newman's boundary condition. And what is electric field? Electric field is nothing but the derivative, the special derivative, the derivative with respect to space of these potential. Okay, so instead of supplying, let's say this is your volume V, which is bounded by surface S. And on each of these surface, instead of supplying you potential, if electric fields are specified. So I should write electric fields are specified on the surface of the. So electric fields if electric fields are specified on the surface of the conductor, and which are obviously, you should understand that electric field is always given by minus grad of V n cap, where n cap is the direction perpendicular to the surface. So you have to normal to the surface. So electric fields are specified on the surface of the conductor, normal to the surface. Because now you have to specify the direction also. If these conditions are specified, okay, so you can say that if the boundary conditions are specified with regards to normal derivative of the potential, then these conditions are called as a Newman boundary condition. And then there can be mixed conditions, which are at times referred to as Cauchy boundary conditions. So I'm not going into depth right now. I'll go once in a while. I'll finish off the topic, which is more significant for your exam. That is method of images. Once that is completed, we'll come back to all these things. Okay. So if there's a possibility that if both of the values, I should write values of potential as well as electric field, or you can say the normal derivatives of the potential are specified. अगर ऐसा है तो क्या होगा? If like values of potential and the normal derivatives of the potential are specified, values of the normal derivatives of the potential are specified, such boundary conditions are given a name called as Cauchy's boundary conditions. Okay. Okay. So uniqueness theorem. In uniqueness theorem, we'll stick to these two conditions. That is, we will be either saying that our potential is uniquely defined at value of the potentials are defined on the surfaces, or we'll be considering the Newman's boundary condition. So whenever we will be talking of uniqueness theorem, okay, so we'll be applying uniqueness theorem to the cases of Dirichlet boundary conditions, where your potential is known on the surface or on the boundary, potential is known on the boundary or on the different surfaces, or electric field is known on the surface or the boundaries. Okay, is that clear? I hope these are just the definition kind of things. Okay, so let us start with some of the very important problem called as method of images. And one should understand this is the direct consequence of uniqueness theorem. So method of images. Okay, and you'll find that each year questions come in the examination from this section also. So let us take, for instance, the charge q on the z-axis, and there's a let's say this is your y-axis, and let's say this is your x-axis. This is x and this is y. And let's say there is you can see that there is a conducting plane here on the xy plane. So this is the conducting plane on the xy plane. This is a conducting plane on the xy plane, and let us ground it. So it is I'm writing here, this is an infinite grounded conducting plane. And whenever something is grounded, you can take that potential to be equal to what? 0. Infinite grounded. Okay, so this potential would be equal to 0. And let us say that this charge is held at distance 0, 0, d of the z-axis. So basically, this charge is at a distance d from the this particular infinite grounded conducting plane. Okay. Now one should understand that since this is a conducting plane, here there's a charge, so obviously there would be some induced charges. So obviously there would be some induced charges. So like there would be some induced charges. And the worst part is that if I need to find the force on this charge q, if I need to find the force on this charge q, I should be in a position to understand what is the distribution of these induced charges. Are you getting my point? So as soon as this charge q is placed here, this is a conducting plane, so it will start inducing equal and opposite charges, and there would be certain pattern to it. I don't know how pattern, or you can say distribution. So some induced charges will start getting, so some charges will start getting induced on the surface of this infinite conducting plane, whose distribution is not known to me, whose distribution is not known, or you can say that this distribution is not known. Okay. Now if someone says that what is the force on charge q, you will be instantly saying to him that you just give me how this charge is distributed, probably then I may be able to help you. Okay, probably then I may be able to help you out, because even if you want to take dq on the surface, you should be in a position to tell what is the induced surface charge density. If you don't know how this charge q is going to play with the like how this charge q is going to bring the charge density on this plane, what sort of distribution is of this induced charges, you will not be in a position to dictate what is the force on this charge q. Okay, so so this is a very complicated problem as such. Okay, so I would write that to understand here, to understand the distribution of charges, to understand the induced charge distribution, understanding the induced charge distribution is a complicated problem in general. Or how is that distributed, and all those things are very difficult to understand. So what we'll do, we'll use something called as uniqueness theorem to the Poisson equation. So we just now told that uniqueness theorem specifies that if you want to find the solution of the Poisson equation or Laplace's equation, in general there are many solutions. if you go back to the lectures of the Laplace's equation, I also showed that a certain Laplace's equation can be satisfied by different other potential functions. So probably I would have taken somewhere some linear function, and then I would have also taken e to the power x square minus y square, and I would have showed that all these are different kind of functions which can satisfy the Laplace's equation. But as I told that in physics, I'm interested in finding those solutions which satisfy a given boundary condition. And what does uniqueness theorem says? That uniqueness theorem says that no two solutions can satisfy a given equation with a specific boundary condition. What does it mean? It means that once if you specify the boundary condition on the surface or on the surface of the conductors or on the boundary itself, then the solution would be unique. Then the solution is unique. So let us see what are the conditions for this particular equation. So one of the so what comes to rescue? But it comes to what we can do is we can utilize the what you can say. We can utilize the uniqueness theorem to solve these kind of problems. Solve these kind of problems. So first you should understand that this charge q in front of this kind of infinite rounded conducting plane is subjected to two conditions. The first condition is that at z equal to 0, or you can say at x on the xy plane, your potential must be 0. Why the potential must be 0? Since the plane is grounded. And second condition that one can clearly see, one can understand that that as potential goes towards as r tends to infinity, your potential must tend towards 0. These two conditions one can instantly take, and it can be understood because see, okay, so as we go as large as possible, if you try to go infinity, one can take this condition that v should tend to 0 as r tends to infinity. Is that clear?
Yeah.
Okay. So in any case, what I'll do is I'll forget this original problem. The original problem suggests that in any case at z equal to 0 plane, my potential must be 0. So I'll forget this problem. I'll write it once so that it's going to be clear. Things again. What I want to do is okay. So I take this. So so this was the problem. Okay. So this was the problem that we were actually stuck in. So what we'll do, we'll forget this problem. And replace this problem by an equivalent problem. So we'll forget this problem and we'll replace this problem by an equivalent problem. And what is that equivalent problem? All we need is because ultimately our potential function would satisfy Laplace's equation, or you can say Poisson equation in general. So this potential must satisfy two conditions. First is that at z equal to 0 plane, your potential should be 0. So what we'll do, instead of this plane, we'll forget about this plane, we'll place a charge minus q. Now, if I place a charge minus q at 0, 0, minus d, and this charge q is at 0, 0, d, so one can understand that if this plane is removed on the xy plane, your potential would be 0. You can see this is at distance kq upon d. This is also at distance kq upon d. This is negative. This is positive. So overall, on the xy plane, you can say that your potential would be 0. So instead of this particular problem, we'll replace this particular problem by saying that instead of this plane, I'll place a charge minus q, and this charge is called as your image charge. And one can understand that why this image charge is important. This image charge is important because, see, if this image charge is placed, then due to the symmetry, one can understand that the potential on xy plane would be zero. Also, you know that the potential due to charges is kq upon x square, or kq upon r. Potential due to point charges is kq upon r. And as r tends to infinity, your potential would tend to zero. Is that clear? So now there is a, I'll say that this, replace this problem. So there will be no conducting plane. Forget about this conducting plane. So there is a, in this new problem, there is no conducting plane. And instead of conducting plane, what we've done, we've replaced this, we have taken, we have deleted this, we don't have this conducting plane anymore. And what do we have then? Okay, what do we have then? We have a image charge. Is that clear? Or is that not clear? I am to bolu फटाफट से. ये तो साला हटेगा नहीं. मानने दो इसको. Okay, I want to keep it simple now. On ठीक है. So instead of this conducting plane, now we have this minus q, which will ensure that the potential on z plane, on xy plane is zero. And because of since these are point charges, and we know that the point charges potential is kq upon r, as r tends to infinity, this will tend to zero. In any case, this potential is, this particular problem can be replaced by this equivalent problem. So this is what we mostly employ, and this is something called as your method of images. Okay, now for this particular configuration, if I want to write potential as a function of r, or as potential as a function of x, y, z, what would be the potential? Potential would be k q upon, let us take any point in space which is like x, y, z. Let us take any point which is x, y, z. What will be the potential due to this charge q? So potential due to this charge q would be equivalent to writing x square plus y square plus z minus d ka whole square. And similarly, I can write minus kq upon x square plus y square plus z plus d ka whole square. Okay, so these are your, this is your potential function, and you can clearly see that. You can also see it from here also, that if I place z equal to 0, if I place z equal to 0, I will get kq upon x square plus y square plus d square minus kq upon x square plus y square plus d square, that is v will be 0. And as r tends to infinity means what? X square plus y square plus z square would tend towards, or you can say it will be very, very, very greater than d square. Okay, or you can say that this is tending towards infinity. So overall, this particular term would go to 0. So this potential is satisfying both of these boundary conditions. Is that clear? Is that clear or not clear?
Yes, sir.
Okay, good. So now, as I told you that, we were interested in finding how this kind of distribution of charge, what is this kind of distribution, like what is the kind of distribution I have? And all it started with saying that if this charge q is placed here, there would be some induced distribution. And because of this induced distribution, obviously this charge q would feel a force towards this infinite conducting plane. And we don't know what is the distribution like. And since we do not know what is the distribution like, then how will we be able to determine the force on charge q? So I told that replace this problem by an equivalent problem. This problem is an easy problem because this contains only 2 point charges, and just that this is almost like a standard 12 problem. So one needs to understand, one needs to find first what would be induced distribution, or you can say induced surface charge distribution. Induced surface charge distribution. One can clearly see that obviously if this charge q is placed, then there would be some negative charge induced, negative minus q induced on the surface. So total charge, we know that it would be minus q, but still we don't know what is the distribution like. So we'll focus on first thing, that is what would be the induced surface charge distribution. Okay, and we know that on the surface of a conducting plane, just outside, the normal component of electric field is given by sigma upon epsilon naught. So normal to the surface of the conductor, just outside the conductor, the normal component of electric field is sigma upon epsilon naught. And what it is like minus del V upon, in this particular scenario, it will be del Z, because the normal component is along the Z direction. Is that clear? This will be equal to the normal component of electric field, that is given by sigma upon epsilon. So sigma would be nothing but it will be epsilon naught del V upon del Z, and just outside it means we are on what plane? We are on the Z equal to 0 plane. So at Z equal to 0. Is that clear? And I know that potential as a function of x, y, z are all given to us. So if we want to differentiate partially with respect to z, what I will get? I will simply get sigma is equal to minus epsilon naught. And I should write, just let me give me a resistor. Okay, so the derivative part will be minus 1 to 2z minus. ठीक है, तो ये हो जाएगा तुम्हारा, I think I will write it here. So minus 1 upon 2 आएगा, एक 2 इधर से आ जाएगा, तो I think 2 कैंसिल हो जाएंगे, z minus d divided by x square plus y square plus z minus d की पावर का स्क्वायर की पावर 3 बाय 2. Are you getting my point? एक तो 1 by 2 because of this आएगा, फिर इसका डेरिवेटिव भी तो 2 आ जाए, and then minus plus q times of z plus d divided by x square plus y square plus z plus d का whole square की पावर 3. Is that clear? So you know that my function and all these things are to be evaluated at z equal to 0, because we want to find the induced distribution of the charges on the plane z equal to 0. Is that clear? This is how.
Yes.
So okay, so induced charge distribution would eventually be a function of x comma y, because your z would become 0, and it is equal to what? It is equal to writing, I think I've forgotten somewhere k also. So k with a kq upon that. So this will be like minus 1 upon 4 pi. And this is minus qz, this is plus qz, this is plus qt, this is plus qd, this is 2 times qd divided by x square plus y square plus d square की power 3 by 2. Or in other words, if I want to express this in plane polar coordinates, because on the xy plane, if even instead of writing x and y, if I want to express my things in r comma theta, then the same thing can be written as sigma r comma theta is equals to minus qd divided by 2 pi r square plus d square की power 3 by 2. So this is your sigma as a function of r comma theta. This is minus qd upon 2 pi r square plus d square की power 3 by 2. Is that clear? So this is how your charge would be distributed. This is how your charge would be distributed on the surface of the conductor. Is that clear?
Yes, sir.
Okay, good. So overall understand, one can also find total charge induced. So what would be the total charge induced? One can expect the answer to be minus q. Let us see if that comes out. So total charge induced on this infinite conducting plane, on infinite grounded conducting. What would be the total charge induced on this infinite grounded conducting plane? It would be equivalent to writing sigma r comma theta r dr d theta integration from 0 to infinite, because r is very, like r is infinitely large. and this will vary from 0 to 2 pi. This will give you total charge induced. So I'll write total charge induced equals to this, and this will be like minus qd upon 2 pi. This is I'm taking it off, and there would be integration from 0 to infinity, integration from 0 to 2 pi, and then I have this r dr d theta divided by r square plus d square की power equal to. So I'll write 2r here, I'll write 4 pi here. So if this is r square plus d square, if you take it t square, then 2r dr would be, if I take r square plus d square as t square, then 2r dr would be equals to 2t dt, and this would be equivalent to writing minus qd upon 4 pi into 2 pi, and this would be right, I think this will be 2t dt divided by t square, so divided by t cube. So 1 upon t square dt, 1 upon t square dt will give you minus 1 upon t, and what is t? Root over r square plus t square from 0 to infinity. Okay, so in any case, you'll get minus q t. If 2 be आना चाहिए था, I have 2 be, sorry. So, समझ पा रहे हो मेरी बात? नहीं समझ पा रहे, गलती हुई क्या?
Yes, sir.
There would be a 2 now. Because 2r dr is 2t dt. So I'll write 2t dt. So this will be minus qt upon 2 pi into 2 upon t. So अच्छा pi भी है 2 pi. So this pi would get cancelled. This would get cancelled, minus q. So your total induced charge would be equals to minus q, and which indeed was expected, right? So your total charge induced was expected to be equals to minus of q. Okay, okay. Now, obviously, because of this induced charge distribution, because of this induced charge on this infinite conducting plane, one can expect that this charge q would experience an attractive force, right? Because this is now negatively charged. I mean, this charge distribution, induced charge distribution on this infinite conducting plane is negative. So obviously, this charge q is going to feel some attractive force. Okay, so let us find this force of attraction which this charge q feels. Okay, so what would be the force on charge q? So I'll write what is the force on the and what would be that force? One can understand, I've already told that instead of this infinite conducting plane, forget about this problem. And now just think about this problem. If this is the problem, and let's say it is at distance 0, 0, z, then instead of infinite conducting plane, you can put a image charge at 0, 0, minus z. So in variable terms, the force would be along minus k cap, and this force would be equivalent to writing k q square upon k q square upon z square minus k cap. Is that clear? Sorry, 2z को समझ पा रहे हो? मतलब ये infinite conducting plane की जगह क्या आ गया? एक चार्ज q यहाँ पर है, this is 0, 0, z, and this charge like this infinite conducting plane would be replaced by this 0, 0, minus z. Is that clear? Now this distance is given by 2z, so your total force would be equal to kq square upon 4z square minus kq. So your force on charge q would be equivalent to this. Is that clear? I mean, all these things are very easy to see. Okay, so in general, as a function of x, and specifically if you have z equal to d, then you can find the force as well. So your force would in general at d at z equal to d would be equivalent to writing minus kq square upon 4d square k cap. Is that clear?
Yes, sir.
I hope it is clear. Okay. Now, what one needs to, what is further, what one can do is, one can also find, I'll write it here. What is the, I'll write it here. What is the work done okay, yeah, but what is the energy of this? What is the potential energy of this configuration? What is the potential energy of this? And now, how do you think that your potential energy is defined? So potential energy is, if I have not done electrostatics, we'll do it lately. I thought that is something that you know already, so I have not done it. So I'll do it on someday. What is potential energy? Potential energy is work, potential or potential energy instead if I write, it is the work done in moving the charge q, work done in moving charge q from infinity to a desired point. And what is that desired point? That is that desired point where the potential or potential energy is expected or is sought. We want to find the potential energy at that desired point. Potential at that desired point. If it is potential, then obviously there should be unit charge. And if I'm saying a potential is work done in moving a charge q from infinity to a desired point where potential energy is required. And you see, instead of now writing this this infinite conducting plane, I will bring this charge q, let's say at any distance z if it is there, and I'm bringing this charge from infinity to a point, let's say d. And instead of this plane, now you can replace this problem by saying that there is no plane as such. Now there is instead of this plane, I have this charge q here, and there is a minus q here. Okay, so there is a minus q here, and there is a charge q here. Now, if this moves. So what is the force that this charge minus q exerts on this? So the force that is exerted on this is equivalent to kq square upon 4z square. Is that clear? So force is in this direction. Is that clear? Okay. So what I'll write, work done in bringing the charge from infinity to this point, so work would be equals to what? It is equals to F vector dot dz vector from so potential is given by work done by external force in bringing charge from infinity to point D, right? So this is minus F vector dz vector. So your dz is in this direction, your F is also in this direction. So I'll write minus integration F modulus dz modulus cos 0, and here I'll get from infinity to D. Is that clear? And then I also know that my dz is decreasing in this direction. So I've already told you that modulus of x is equal to what? Modulus of x equal to minus of x if x is less than 0. So if your particle was initially at infinity and now you're bringing towards D, so obviously your dz has to be negative. Only then it can come in this decrement side. Like only then it can get decreased. Are you getting my point? So whenever you move towards the origin, this dz would be less than 0, because dz represents the increment. This is not increment, rather this is decrement. Only then you can move from infinity to point D. So this is like minus infinity to D, and here you can write kq square upon, I think, 4z, and this dz would be minus dz. So this dz minus would get absorbed, and this is it. And it is easy to find this work done. So work done would be equals to what? It will be equals to kq square. Sorry, I think z square over here. So this will be minus 4z from infinity to, so minus kq square upon. Obviously, this is the because whenever your system, this is the potentiality of the system. So whenever your system has an attractive thing, this is the binding energy which is required to. What is the binding energy required to dismantle the system? इतना ही negative amount of energy दे दोगे, this system would dismantle. Is that clear? ये चीज समझ में आ गई? Okay, good enough. So I think it's quite enough for today.
सर
हाँ बेटा बोलो.
सर ये जो फोर्स हमने लिखा है डायरेक्ट के क्यू स्क्वायर में 4d स्क्वायर नहीं लिख सकते?
ना 4d स्क्वायर नहीं लिख सकते, because we have to find potential energy. Potential energy क्या होती है? it is work done by the external force in bringing charge from infinity to point D. So we'll have to take it variable. We'll have to take it variable. And while we bring it from infinity to point D, so your force has to be FdZ because your force is dependent upon Z. Now you bring it from infinity to D, so obviously you will have to take this force as a variable function.
सर
अगर
फिर
इसको
इन्फिनिटी टू डी लाएंगे तो पॉजिटिव चार्ज है वो जो हम लाते हैं टेस्ट चार्ज, तो उसमें तो क्यू स्क्वायर नहीं आना चाहिए ना, सिर्फ एक क्यू आना चाहिए, दूसरा तो प्लस वन ही है।
मैं नहीं समझा, सॉरी, क्या बोलना चाह रहे हैं? एक्चुअली देखो, पोटेंशियल अलग चीज होती है, पोटेंशियल एनर्जी अलग चीज होती है। पोटेंशियल इज वर्क डन इन ब्रिंगिंग अ यूनिट चार्ज फ्रॉम इन्फिनिटी टू अ डिजायर्ड, वो होता है पोटेंशियल। जैसे फील्ड और फोर्स में अंतर होता है, फील्ड क्या होता है? इट इज द वर्क, इट इज द फोर्स पर यूनिट चार्ज, राइट?
यस सर।
है ना? ऐसे ही पोटेंशियल एनर्जी क्या होता है? इट इज वर्क डन मूविंग चार्ज क्यू फ्रॉम इन्फिनिटी टू डिजायर्ड पॉइंट। सो इंस्टेड ऑफ इलेक्ट्रिक फील्ड हियर ही विल हैव फोर्स वेक्टर। आई
यस
डोंट नो,
सर।
मतलब कहाँ अटक गई गाड़ी?
सर मतलब मैं तो ये सोचा था डायरेक्ट हमने फोर्स कैलकुलेट कर ली थी दोनों चार्ज के बीच में,
हम्म।
तो सीधे अगर मैं एफ डॉट डी जेड कर दूंगा तो वो आ जाना चाहिए ना मेरा वर्क डन। और दोनों चार्ज के बीच में फोर्स जो है वो तो कांस्टेंट है, मतलब उसमें जेड की जगह डी ही आएगा, टू डी स्क्वायर, तभी फोर आया था वो नीचे।
हम्म।
तो मैं सोचा था उसको जेड को वेरिएबल बोला, आपने वो बताया ना इन्फिनिटी से डी लिया इसलिए वेरिएबल कंसीडर किया। ठीक है सर,
राइट।
क्लियर है वो।
Okay, okay. Chalo. Okay. So we'll meet probably on Monday now. Okay.